So you don't have to copy this slide down. We've seen it before. Okay, we introduced it last section when we were talking about an identity matrix. An identity matrix only occurs in a square matrix. And an identity matrix for a square matrix is one that has diagonals. The main diagonal is all ones and everything else is zeros. So because it's only a square matrix, a 2 by 2 identity matrix will have ones on its main diagonals, zeros everywhere else. A 3 by 3 square matrix will be 1 0 0 0 1 0 0 0 1. 4 by 4 square matrix has an identity of this. And we could keep going ad nauseum, right? We're all cool and understand what an identity matrix looks like. Okay, so then the reason that we want to know what the identity is because we want to know its relationship to the relationship between a matrix and its inverse. Okay, so let's first of all talk about inverses for other operations that we know. Okay, what is the inverse for multiplication? Division. Okay, or multiplying by a reciprocal, right? So let's say that we want to talk about the number x over 4 equals 5. And we are trying to solve for x. Okay, what would we do? The opposite of division is, so the inverse operation would be multiplying. So if we do the inverse operation of multiplying this side by 4, we also have to perform the inverse operation on the other side, don't we? We have to do a 4 times that 5. Okay, multiplying by 4 is the inverse of dividing by 4. What will we get on the left side? X. But it's not really just x, it's 1x. Okay, 1 is the identity for multiplication. Okay, we'll take anything times 1, we get itself back, right? So that's the identity for multiplication. And so we would end up with 1x equals 20. Okay, so far so good? Okay, let's talk about identity for addition. Identity for addition, let's say that we have 3 plus x equals 7. We're trying to solve that basic equation. What would you do to do the opposite, the inverse of addition? Subtraction. So we would subtract 3 from both sides. Because subtraction is the opposite operation, right? The inverse operation of addition. So what would we get over here? X, right? But it's not really just x, it's 0 plus x equals 4. 0 is the identity for addition, right? We can add 0 to anything and get itself back. So 0 is the identity for addition. Okay? So we're using the inverse operations in order to be able to find the identity times something or plus something equals an answer. So far so good? Okay, so now that we've taken that back to its fundamentals, we're going to talk about how if we have a matrix A, okay, and we take this matrix A times its inverse, okay, just like when we took this times its inverse, we should get the identity times, or the identity back, okay? And it doesn't matter the order in which we multiply this. If we took the inverse of A times A, we still also get the identity matrix back. So far so good? Questions over this? All right, so you have to remember to call this A inverse. Okay, it's not a negative 1 power. All right, so we want to show that B is the inverse of A. So how would we do that? 2 matrices up here, 2 square matrices. How do we show that one's the inverse of the other? How did we show that 4 and 1/4 are inverses of each other. We multiplied them, right? So let's multiply these two matrices together. When we multiply them, what should we get? Should get the identity. Okay. So last year, some of your teachers taught you to write B up here. We're multiplying them together. And put A down here, because that can aid you in multiplying them. And your result is going to go here. Okay. So if we say this is my first row, first column, that means that we're taking the first row times the first column. So 4 times 4 is 5 times negative 3, 16 plus negative 15. Now we're in the first row, second column. So 4 times negative 5, 5 times 4, negative 20 plus 20. Second row, first column. 3 times 4, 4 times negative 3, so 12 and negative 12. And 3 times negative 5 for our second row, second column. 4 times 4, add them up. So we got the identity back. Okay, that was by taking A times B. Okay, you need to see it the other way. You can take B times A and get the same thing. Or are you convinced? Okay, all right. So now, how does that work? Well, we understand how it works, but we want to see how would we get an inverse. Okay, they gave us two matrices, said these are, show that these are inverses, right? So we want to actually be able to come up with the inverse itself. Okay, such that when we take it times the identity, or times the original matrix, we get the identity back. So our process is, if we have a square matrix of the order n by n, we write the matrix with the identity matrix on the right. In other words, we're kind of augmenting this matrix. We put the matrix here, we put our little dashes, and then we put our identity to the side of it. Okay? If possible, we're going to row reduce A to I using elementary row operations. We can switch rows, we can multiply number by the whole row and add them together. We can divide, we can multiply every single item by the same number, or divide in our case, many times we call that. And we check our work by multiplying A times A inverse. Bless you. Okay, so that's the process. So we have this little 2 by 2. If we write this 2 by 2 with its identity appended to it, we're going to get what? And if you want to put the dashes there to keep things in line and order, feel free. If you don't, I'm not going to count it wrong. Okay? So we have our new matrix that we're going to be working with. What are we going to do to it? Basically trying to do row operations to get the identity over here. And what's on this side then will be the inverse. Okay? So what can we do to try to get the identity on the left-hand side? Good. Let's add row 1 and row 2 and put it in row 2. I'm probably going to run out of space. Let's put it down here. So 1 plus negative 1, negative 2 plus 3, 1 plus 1, sorry, 1 plus 0, and 0 plus 1. Okay, let's rewrite our top row. All right, now what do we have to do to get the identity on the left? We get rid of what? That negative 2. So how can we get rid of a negative 2? Yep, R1 plus 2R2. Going into R1. All right, so let's think about what this will be if we take 2 times this whole row. We're just doing pencil marks here. We're not replacing anything. We're just penciling those in so we know what we're adding. We're going to add 1 plus 0, negative 2 plus 2, 1 plus 2, and 0 plus 2. Rewrite our second row. And we now have the identity on the left and our inverse on the right. Okay? Let's verify that these are, in fact, inverses of each other. Okay? So to do that, we need to take A times A inverse. So if A is, let me do this in different colors so we can see that we're separate process here. A is 1, negative 2, negative 1, 3. A inverse, we think, is up here a little higher. We think it is 3, 2, 1, 1. So what happens when we multiply them together? So this is the first row, first column, right? So our first row times our first column. 1 times 3, negative 2 times 1. Add them up. First row, second column. 1 times 2, negative 2 times 1. Add them up. First row, second row, first column. Negative 1 times 3, 3 times 1. Add them up. And second row, second column. Negative 1 times 2, 3 times 1. Add them up. So A inverse is 3, 2, 1, 1. There is another way for a 2 by 2 that is faster than this. Okay, so I'm showing you the process because it doesn't work on a 3 by 3. Okay, and I'll show you the 2 by 2 of the other method, alternate method. Okay, so you probably have already noticed or may have recognized it. Okay, so far so good. Okay, this works for 2 by 2, works for 3 by 3, works for 4 by 4. We won't ask you to do an inverse of a 4 by 4 or anything like that. But it works for every type of matrix, every type of square matrix, if the inverse exists. Okay, so far so good? Okay, now, next part then says, let's try it on a 3 by 3. Okay, because there isn't another method, an easier method, until we get further into this. Okay, so what's the first step? Put the identity on the end, right? Okay, so we're going to start with 1, 1, 1, and then we add a 1, 0, 0 on the end, right? 3, 5, 4, 0, 1, 0, and 0, negative 1, 0, 0, 0, 1. Okay, now we got to get this guy into reduced row echelon form. Anybody else really liking this row? Row 3. You know how nice that is. But where should it be? Row 2. Does everyone see why? Okay, what would we have to do to it to make it perfect? Multiply by negative 1 and put it into row 2. Okay, we can switch rows. That's legal, as long as we switch the whole row. So this guy's going up here. We're going to take a negative 1 times row 3 and put it into row 2. So we would get a 0, 1, 0, and then a 0, negative 1, 0. Oh, sorry, 0, 0, negative 1. Thank you. Trying to switch things up. I shouldn't have been. Nothing else has changed except for the sign and its position. Okay. Can we leverage this old row 3 to help get a 0 someplace else? In row 1, right? Okay. So what are we going to do? We're going to add that old row 3 to row 1, and we'll get a 0 up here. Or maybe we should continue to focus on just getting zeros in this corner. Okay, let's do that first. Okay, so how are we going to get a 0 in place of this 3? Top row times negative 3, adding it to that old row 2, going into row 3 now. Okay, so we're going to take row 1 times negative 3, adding to what was row 2, and it's going into row 3 spot. So let's put the pencil marks in there. We're not changing that row, just helping ourselves so we don't make a mistake on doing our multiplication. So we're taking 3 times everybody in this top row. 3, 3, 3, 3, 0, 0. God bless you. Okay, we're going to add it to this 3, 5, 4, 0, 1, 0 and put it in the bottom row. Okay, so 3 plus 3 and 3 plus 5. Oh, sorry, these are supposed to be negative 3s. Thank you. My fault. Negative 3. Okay, so 5 minus 3, positive 2, right? Okay, 4 minus 3, 0 minus a minus 3. Or, wait, we're just adding. 0 plus negative 3. Negative 3, 1 plus 0, and 0 plus 0. So we're adding, okay? Initially was trying to make us subtract. Okay, doesn't have to be that hard. All right, so now we've got a 0 there, okay? Next we need to probably work on that 2, right? Let's put our dashes in there so we don't confuse ourselves. So how can we get rid of this 2? Okay, if we take the top times negative 2, we're going to get a negative 2 in this spot. And negative 2 plus 1 is going to get us, we're undoing our 0 here. Not the top by negative 2, but the middle by negative 2. See why? Okay, so we're going to take row 2 times negative 2 and add it to row 3. And put it in row 3. Okay, so pencil marks again. 0 times negative 2, 1 times negative 2, 0 times negative 2, 0 times negative 2, 0 times negative 2, negative 1 times negative 2. So 0 plus 0, negative 2 plus 2, 0 plus 1, 0 plus negative 3, 0 plus 1, 2 plus 0. And our middle row is perfect as well. So we have one more to work with. So how are we going to get rid of this one? Top row minus second row, right? Row 1 minus row 2. So 1 minus 0, 1 minus 1, 1 minus 0, 1 minus 0, 0 minus 0, 1 minus a minus 1. Last step, we have to get rid of one more 1. What are we going to do? Row 1 minus row 3. So 1 minus 0, 0 minus 0, 1 minus 1, 1 minus a negative 3, 0 minus 3, or 0 minus 1, and finally 1 minus 2. A lot of paper, right? So what is the inverse for matrix A? This, right? 4, negative 1, negative 1, 0, 0, negative 1, negative 3, 1, 2. And we would verify by multiplying A times A inverse or A inverse times A, and we better get the identity back. Okay? They may need to see the multiplication. Are you okay? Okay, question. Mm-hmm. Mm-hmm. We didn't have to change anything in this one at the time. We just tried to save some paper. Yeah, so we can simply swap rows and call it good. We could have switched this one here and this one here, and then moved on. I didn't know how much space I would have on my board. Well, if you ended up, it wouldn't be in its identity form. See what I mean? If this was still 0, 1, 0, then it wouldn't be an identity matrix on the left-hand side. So you'll eventually have to. So you could have, so I see what you mean. Okay, so could we have taken 3 times this top row, negative 3 times the top row, and get a 0 here, right? Mm-hmm. Yeah, you could. Absolutely. You would, you're going to end up introducing numbers here, right? And that you'll have to get rid of eventually. So if we recognize that this was pristine, this is exactly what it should be for row 2, it's probably better just to put it in that spot. It'll save you time. But it's not necessarily the right way. It's just a way. You can still get the right answer the other way. Okay? Other questions on this one? Okay, so let's show you the shortcut for the inverse of a 2 by 2. And you can use either one on the quiz on Thursday. Okay? So to find the inverse of a 2 by 2, only works for 2 by 2, not 3 by 3, not 4 by 4, and so on, is if we have a matrix A that has elements that are A, B, C, and D, and AD minus BC is not equal to 0, then the inverse for this 2 by 2 exists. And it's written by as 1 over AD minus BC times a mixed up matrix. Now, the reason it can't be equal to 0 in this is because it's going to the denominator of a fraction, right? We can never ever divide by 0. If we're trying to divide by 0, that means the identity, it does not have an inverse. There is no matrix that you can multiply by it to get the identity back. Okay? Now, this AD minus BC is called the determinant of a matrix, and we'll learn more about that on Friday. Okay? So, if you're trying to find the mixed up or the inverse matrix of this original, what you do is you find your determinant by multiplying downward, A times D, multiply on the main diagonal, multiply on the opposite diagonal. We usually write B first, but we change the sign, and then we add them up. Okay? Then we put that in the denominator of a fraction, and this is going to be a scalar multiple of our new mixed-up matrix. To get the mixed-up matrix, we switch the A and the D around, and we change the signs of the B and the C. So we switch the main diagonals, and we change the sign of the minor diagonal elements. Okay, so far so good? All right. So let's see if we can find the inverse of this matrix. Okay. So first of all, we have to see if it even exists. So we're going to do what? So 5 times 4 is, and 3 times a negative 1. But we're going to change the sign and add them up, and we'll get 23. So 23 goes in the denominator of this fraction. That's our scalar multiple of our mixed up matrix. Sure, that looks like a 3 and not an 8. Okay. So when we mix up our matrix, what's going to be the new element up here in the first spot? 4. What's going here? Positive 1 here, negative 3, and here 5. And then we just take 1/23 times everybody. So we'll have scalar multiplications like distributed property, right? 4/23, 1/23, negative 3/23, and 5/23. If we take this times A or A times this, we should get our identity back. Yes? Okay, so far so good? All right. Do you believe me, or we want to multiply it out? You want to take your time for no reason? Okay, we believe. Okay, graphing calculator to the rescue. One last slide. All right, remember these problems from last chapter? Okay, we're investing $15,000 in AAA, AA, and B-rated bonds. Okay, municipal bonds again. So Omaha, I think, still has its AAA rating. It's a pretty good risk that the taxpayers are going to pay their taxes, and therefore you're going to get your money back, right? So if they want to do a sewer improvement project or something, they may be a AAA rated bond, which means that you wouldn't get as much interest on their bond, right? 3.5% interest, they're less risky. Someone else might be a little bit more risky, or the different kinds of loans, life of loan and so forth. There's lots of reasons for them to give a different interest rate. But you can make 3.5% on the AAA bond, you can make 5% on the AA, you can make 6% on the B bond. Okay, B is the riskiest or a little bit more scary, so you're going to make more money on it. Okay, so we know that we're adding x plus y plus z, however much we're investing in the 3.5, the 5 and the 6% bonds, 15,000. 35% times the amount we invest in this one, plus 5% times the second, plus 6% times the third, gives us our mixed up percentage, right? Our combined percentage times that 15,000, which is then going to end up being $720 in interest that you're making. And then they said they are investing twice as much on the AAA as a AA. So to make them the same, x would be equal to 2y. We bring it over to make it into a nice standard form of equation. Okay, so we've got this lovely equation. How can we use matrices to solve this now? Because these were not fun to do the other way, right? Can we write a matrix equation? Okay, what would our matrix equation say? Beautiful. All right, so there's our coefficient matrix. What's it being multiplied by? Yep, our variable matrix. And what's our answer matrix? Yep. Okay? Now, based on what we know about matrices and inverses and identities, what do you think is going to happen? How can we use an inverse matrix to solve this? Not how to find it, because we're not going to find this the hard way. We're going to use graphing calculator. What did we use before for our little multiplication problem? Yeah, well, not so much the augmented, but remember just a little bit ago we had something like 1/4 x equals 2, right? And we wanted to solve that. What did we multiply this by? The inverse, right? Which gave us the identity, right? So if we can find, if this is A, this is X, and this is B, if we can take A inverse times A, we better get the identity back, right? And what would that identity look like? Okay. So we take that times our XYZ, and 1x plus 0y plus 0z is x, right? 0 times x plus 1 times y plus 0 times z is y. 0 times x plus 0 times y plus 1 times z is z. Okay? But if I multiply the identity, the inverse times one side of the equation, I've got to do the same thing on the other side, right? Does that make sense? Balance our equations, we got to keep it the same. Okay? Now, why did I put A inverse times B instead of B times A inverse? What's the order of A inverse? 3 by 3. What's the order of B? 3 by 1. Do you see that we have to have A inverse times B to get our result? Otherwise, we can't multiply them if they're out of order. A 3 by 1 can't be multiplied by 1 by 3, or by 3 by 3. Okay? So far, so good? Okay. So our idea then is that we're going to find the inverse of A, and we're going to multiply it by B, and we'll have our answer. Okay? So graphing calculator's out. Here we go. All right. So to plug this in, curious to see if alpha F3 works. Nope, doesn't on this one. All right, to plug this in, we're going to go to the second of the inverse button to get to matrix. And we need to edit our first matrix. We're going to arrow to the right and edit matrix A. And this matrix needs to be 3 by 3. Okay, so then put your matrix A in there. Now we're going to quit and edit matrix B to have our 3 by 1. And put these guys in here. So 15,000, 720, and 0. So now we said to make this work, so that we don't have an error or a problem, we need to take our A inverse times our B. So we quit. Okay. And we go get A inverse. So second matrix This time we want the name. We want to go get A. And if we want its inverse, we're going to use the inverse button. Looks like x to the negative 1, but it's not. It's the inverse button. So we hit the inverse button, and we can put a time sign in there, but we don't have to. And we can simply say, go get matrix B now. So second matrix, and go get B. So it's saying, let's take A inverse times B, and we press enter, and now we know how much money to invest in each. On the test, you won't get to use the graphing calculator. We'll have you practice this for some certain things. For the ACT, of course, you get to use it, but for this type of problem, no. There'll be a calculator and a non-calculator portion. So if we give you something that's difficult, yes, well, by all means, we'll let you. I haven't, based on last year's test, no, we didn't do it. But I may change it, modify it for this year. Last year I didn't have as many students with graphing calculators. How many people still don't have one in here? Does everybody have one? Okay, one, okay. So it's possible that we could do a graphing calculator portion. All right. We'll see. We have our calculators ordered, so we'll see as soon as they show up too. All right, so far so good. Now what if we wanted to see what that matrix inverse looked like, right? We can go in here and say, hey, I want to see that matrix. So I want to go back to my entry, second entry, and I basically want to just back off and hit delete for this B so I can see what the inverse matrix looked like. So we press enter, and it doesn't look very pretty, right? But we can see what it's in fraction form because that's sometimes better. And so you can click on math or press math, and then you can say, tell me that in fraction form, and you press enter again, and it tells you that it was 2, negative 100 over 3, 1/6, 1, negative 50 over 3, negative 5/12, and so on. So you can get it in fraction form too. So questions on this one? All right, the idea is make a matrix equation, which we've been doing for a little bit now. Find the inverse of A, and take that times our answer matrix. And away you go. All right, assignment.